Barnard's star is the closest single star to our own Sun, just under 6 light-years away, close enough that it's practically a next-door neighbor by galactic standards. It has 4 confirmed planets, and astronomers just finished the most detailed portrait of that system anyone has ever produced. The conclusion couldn't be more different from the LHS 1140b story making headlines the same month. This is what a close neighbor looks like when almost everything that could go wrong does. Barnard's star itself is ancient, a small, dim red dwarf roughly 10 billion years old, more than twice the age of our own Sun, quietly orbited by its planets since long before Earth's own continents had finished forming. Astronomers have chased planets around it for decades, and for just as long kept getting it wrong. Claimed detections came and went throughout the 20th century, each one eventually failing to hold up under closer scrutiny, turning Barnard's star into something of a running joke among planet hunters long before anything was confirmed. It wasn't until extremely precise instruments called Espresso and Marunex finally nailed down real, confirmed measurements, with 4 separate planets identified between August 2024 and March 2025. These weren't planets that fit neatly into categories we already knew. Every one of them falls into a mass range between Mars and Earth, a size class that doesn't exist anywhere in our own solar system at all. Here's where the story turns bleak fast. All 4 planets orbit absurdly close to their star, packed into a region spanning just 1 to 4% of the distance between Earth and the Sun. To put that in perspective, even the outermost of the 4 orbits about 10 times closer to Barnard's star than Mercury orbits our Sun. At that distance, every one of these planets has become tidally locked, the same fate that keeps one face of our Moon permanently pointed at Earth. Each planet shows one hemisphere in permanent daylight, and one hemisphere in permanent, unbroken night forever, with no sunrise or sunset ever crossing the boundary between the two, no matter how long you waited there. Squeezing 4 planets into an orbital space that tight should be a recipe for disaster. Systems packed this closely together are usually unstable, prone to gravitational interactions that eventually fling planets into their star, smash them into each other, or eject them from the system entirely. Barnard's star's 3 inner planets avoided that fate through a specific kind of gravitational choreography, an orbital resonance, where their orbital periods lock into a precise, repeating ratio. In this case, 9 to 12 to 16. A close cousin of the same resonance that stabilizes 3 of Jupiter's largest moons, Io, Europa, and Ganymede. That resonance is very likely the only reason this fragile, tightly packed system hasn't already torn itself apart over the 10 billion years it's had to do so. None of that on its own would have been enough to call these planets hopeless for life. Plenty of tidally locked, close-orbiting worlds remain genuinely interesting candidates elsewhere in the galaxy. And Barnard's star itself isn't unfamiliar territory for this exact kind of hope. Back in 2018, a different claimed planet in this same system, Barnard's star B, briefly generated real excitement precisely because it sat just beyond the star's frigid snow line, the boundary past which water ice could theoretically persist on a planet's surface. That particular claim later failed to hold up under further scrutiny. One more entry in this star's long history of promising leads that quietly evaporated under closer observation. This time, the 4 confirmed planets are unquestionably real, and the verdict on them came from a team at the University of Cambridge, led by astronomer Xander Byrne, who took a different approach entirely. Instead of studying the planets directly, which remain extraordinarily difficult to observe up close, even with today's best instruments, They analyzed the chemical fingerprint of the star itself. That approach works because of a basic fact of planet formation. A star and the planets that form around it are built from the exact same original cloud of gas and dust, meaning the chemistry of the star offers a genuine window into the chemistry of its planets, long before anyone can study those planets directly. What Byrne's team found was a star carrying an unusually large amount of magnesium compared to typical stars its size. On Earth, magnesium overwhelmingly ends up locked inside a mineral called olivine, a mineral that plays a critical role in storing water deep within a planet's mantle over geological time. But Barnard star's specific chemical ratios, an unusually high magnesium to silicon balance, alongside other trace elements, point somewhere else entirely, toward a mineral called periclase instead, magnesium oxide, a mineral essentially incapable of storing meaningful amounts of water at all. The consequences cascade from there. A periclase-dominated mantle holds less than half the water capacity Earth's mantle does. It also generates only about half of Earth's own internal radiogenic heating, the natural warmth produced by decaying radioactive elements that keeps a planet's interior geologically active over billions of years. Less internal heat means less volcanic activity, and less volcanic activity means far less capacity to outgas any kind of secondary atmosphere, even billions of years after a planet's original atmosphere has been stripped away by its star. And stripped away is exactly what happened. Being locked this close to any star means constant, punishing exposure to high-energy radiation, more than enough to blast away a thin, young atmosphere entirely within a relatively short span of time. Byrne's team ran detailed atmospheric evolution models, testing a wide range of possible planet masses, densities, and starting atmospheric conditions. The result held steady no matter which reasonable assumption they tested. Every single one of these 4 planets would have been completely stripped of any original atmosphere within roughly 2 billion years. Barnard's star system is roughly 10 billion years old. These worlds have had 8 billion additional years, at minimum, to somehow build something back from volcanic activity alone. Their own interior chemistry made sure that never happened, sealing their fate twice over. Once from the outside, radiation stripping away whatever atmosphere existed early on, and again from within, denying any real chance of ever rebuilding one. There's a genuinely useful takeaway buried inside this otherwise discouraging result. Byrne's team emphasizes that linking a star's own chemical composition directly to its planet's likely habitability gives astronomers a real, practical shortcut, a way to flag which nearby systems are worth the enormous effort of detailed follow-up study, and which ones can be reasonably deprioritized, well before dedicating years of expensive telescope time chasing planets that were likely doomed from the moment they formed. Upcoming missions like the European Space Agency's Plato, designed specifically to hunt for smaller, rocky worlds that current instruments still struggle to detect reliably, stand to benefit directly from exactly this kind of chemical shortcut, letting scientists prioritize their limited observing time far more efficiently than simply checking every candidate one star system at a time. Barnard's star sits close enough that it's practically part of our own cosmic neighborhood. 4 confirmed rocky planets orbiting a star we can study in exquisite detail from right here on Earth. And the answer, this time, isn't ambiguous or still up for debate the way so many exoplanet stories tend to be. It's written directly into the star's own light. Too close, too tightly locked, and built from exactly the wrong chemistry to ever hold onto the one thing that might have made any of it matter. Sometimes the universe answers the habitability question by shouting yes. However cautiously, the way it just did with LHS 1140b. A hopeful signal from 48 light-years away. And sometimes, right next door, close enough to practically touch by cosmic standards, it simply answers no. Beyond the visible, beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel, new episodes on space, physics, and the edges of what we understand, with new content going up every day.